So let's now try to derive the first form of this Chernoff bound. And by the way, in passing, I just want to mention that people might use the phrase tail bounds sometimes to mean bounds of these sorts. Because the idea there is that as you go further and further away from the mean in the distribution, you are getting towards, away from the head, let's say, towards the tail of the distribution. That's the intuition of why you have that term floating around, although formally these are called deviations or deviations from the mean. So what is the form of the Chernoff bound that we are trying to now prove? So continuing with what we saw before the pause, you have n independent Poisson trials. The trial I will give you a value 1 with probability pi, and now we want to take a measure of the sum of n such trials, and mu is the symbol used to denote the expectation of x. Okay? So the form of the bound, I said the first case is what we will work through now, takes this form that for if you give me some value delta, which is bigger than 0, then the probability that x is bigger than or equal to 1 plus delta times the mean, mu, that far away from the mean, is less than e power delta whole thing raised to the power mu divided by 1 plus delta raised to the 1 plus delta. There are different forms of this bound that people see. I, in the previous discussion, showed 3 cases. This particular form is very useful, and we will look at that form in some detail in the next few minutes. So how do we show that this is true? So there is one additional concept from the basics of probability that we need to know in order for us to be able to prove this, and that is the concept of a moment generating function. So it's a concept that we will introduce, define now, and use it to actually derive the bound. So as before, we have our favorite Poisson trial sequence. I'm repeating here just to be completely local with notation. It's exactly the same of what you had before. And let mu, which is the expectation of x, right, is simply sum over I going from 1 to n, the expectation of the individual xi's, which is nothing but the sum of I going to 1 to n, pi, because these variables take on a value 1 with probability pi and a value 0 otherwise. Now, that's just something we'll hang on to on one side. And now we have the moment generating function of xi with a parameter t that we will find useful to work with. And that's a definition. We'll just take it as something that exists. But how does it look? It's simply the expectation. Instead of talking about xi, we talk about e to the power t xi. So if we look at this for a little bit, we know that the xi takes on a value 1 with probability pi. So it's pi, and if this takes on a value 1 times e power t, takes on a value 0 with probability 1 minus pi, and e power 0 is 1. So it's 1 times e power 1 minus pi. And just simplifying it, you get 1 plus pi times e power t minus 1. And noticing the well-known fact that 1 plus x less than equal to e to the x, we can rewrite this as less than equal to e power pi times e power t minus 1. Now this form is called the moment generating function of xi with that bound known for it. So mxit, which is the expectation of e power txi, is less than equal to e to the pi times e to the t minus 1. That's something we'll use. So For x, the random variable, the moment generating function x, again with the parameter t, is simply the fact that each one of the xi's are 1, and therefore it is the product going from 1 to n of m sub xi's of each of the xi's with the parameter t. Okay? Which is using the value that we knew from the previous slide, the derivation that showed what mxit is. Therefore, it's less than equal to the product, and this is a pure substitution for mxit from our previous slide. And that is simply, if you look at this product form, it is e, the exponential of sigma, which is the sum of the pi's, because if you look at a product of many of these terms, it is the sum, using the basic laws of indices, it is the sum of the exponential values. So we are just saying it's e raised to the sum of these values, and e raised to the sum of those values, if you make the additional observation that we are summing over all the pi's, this value, it is therefore that becomes mu, which we know, sum over all the pi's. So it's simply e raised to the e to the t minus 1, this term, times mu. So what do we have? mxt is less than equal to e raised to e to the t minus 1 times mu. So what do we really want to prove? We want to prove a bound on the probability that x is bigger than 1 plus delta times mu, okay, which is equal to the probability here, just exponentiating both sides, because you can just raise both to the power e, the left hand side raised to the power e raised to the left hand side times t, you're doing exactly the same to the right hand side. And since e, these are positive values and e is an increasing function, we would be able to essentially preserve the inequality. Okay? So now, if you look at what's inside this probability function, and using Markov's inequality, we get this substitution. But we do know that expectation of e power tx can be rewritten from the previous slide in this form, e power e to the t minus 1 times mu. Now, given that we have delta greater than 0, let us just pick, t was an unbound parameter, we didn't fix a value to it. So we fix a value of t equal to log 1 plus delta, and we get the form, each time if you write log 1 plus delta, then you get, if you replace t there and t there and simplify, we get this form here, which is simply e to the delta times mu divided by 1 plus delta raised to the 1 plus delta. So basic algebra, only interesting two observations to make: what the bound we derived through the moment generating function in the previous page, and replacing this inequality, what we want, with the same inequality using the moment generating function form. And once we have that and apply Markov's inequality, the algebra, very simple algebra actually, gives us the rest. So what we are essentially saying is, the further away we get from the mean, if we ask the question, for example, if this arrow goes further and further out, the area under this curve, the distribution, to the right of the arrowhead is decreasing exponentially. So you're capturing most of your value to the left of the arrowhead, and that's symmetrically true going to on the negative side as well. So that's really what we are trying to do by way of bounding the probability that you are within a certain distance by actually calculating the probability of what it is to be away beyond that distance. So that ends the calculation of this particular form of Chernoff bounds. We may be looking at the other forms possibly through exercises just for practice. So with this, the elements we need from the basics of probability and the bounds that we need are known to us now. So now moving on to the next lecture, we'll be switching back and talking about applying these notions to what we were doing just before we started on this somewhat of a digression into the basics of probability, machine learning. Thank you.